Back in the early 2010s, I had a challenge. Our family had recently moved from Texas to Pennsylvania. We had started a small orchard with as many fruits as I could hope to grow. Along with the normal fruits like apples, pears, blueberries, raspberries, and peaches, we planted pawpaws, persimmons, kiwi berries, and jujubes. We also planted a number of fig trees, knowing that most winters here in Pennsylvania they'd be knocked back to the ground and would have to regrow from the base each spring. And that's where my challenge came in. When we lived in Texas along the Gulf Coast, we could grow a number of interesting subtropical fruits like figs, some variety of citrus, and even some hardier avocados. Now we lived in Pennsylvania, and growing these fruits out in the open, unprotected, was out of the question. In order to grow any of these fruits reliably, I'd need to protect them in some way, and because they wanted a long growing season, I would somehow have to give them a climate similar to the Gulf Coast or Southern California. In short, I'd need to grow them in a greenhouse. When I look back on it, I was facing three main challenges in planning for a subtropical greenhouse for figs, citrus, and avocados. First, and this probably goes without saying, the greenhouse would have to be effective. Many of the plants I was wanting to grow could withstand brief temperature drops into the low 20s or perhaps the high teens, but nothing could withstand drops into the single digits or multiple days in a row below freezing. So the greenhouse could experience some freezing, but would need to rebound quickly. And also our normal growing season outdoors is around 180 frost-free days. If I could extend that to 270 or 300, it would definitely help the figs that want a long and hot growing season. Second, the greenhouse couldn't break the bank to build. When I started looking at possible greenhouses, especially those that were more energy efficient, it quickly became apparent that the upfront cost to build increased dramatically the more energy efficient or specialized the structure was. More on that later. Finally, third and related, the greenhouse couldn't break the bank to operate. If a greenhouse is inexpensive to build on a per square foot basis, but expensive to operate due to heating costs or maintenance cost, then we're just paying what amounts to a tax over time for not building a better structure. Around the time that I conceived of the idea of a subtropical greenhouse, I was working as a software developer. As a software guy, I didn't know anything about greenhouses, but my nerdy superpower was that I knew how to research everything to death. So I started researching possible greenhouse solutions that met the three challenges I mentioned previously. Let me first dispel a common misunderstanding I had, and maybe you have too. I had the mistaken impression that simply placing a greenhouse structure over the ground, I would gain an advantage over the temperature outside. I figured this would buy me at least 5 to 10 degrees, maybe more if I was lucky. It turns out that this really isn't true, and it comes down to the insulation value of most greenhouses. Insulation value, meaning the resistance to heat loss, is typically measured in R value units. You might see this if you ever buy a roll of insulation for your house, and I won't dive into specifics, but insulation value increases as the R value number goes up. Most modern homes have insulation value in the walls north of R10 and higher for the roofs. By comparison, a normal greenhouse has an R value of less than 2, and on top of that, it's not nearly as air sealed as a house, and has framing made of a heat conductive material, namely the piping, all of which contribute to heat loss. This lack of R value in a greenhouse means that after the sun goes down, even a well-sealed greenhouse will rapidly lose most of its heat to the surrounding atmosphere. In winter, when the nights are more than 12 hours long, the possibility of retaining some heat overnight just isn't workable. Without some form of added heat, the temperature in the greenhouse drops to within a degree or two of the outside temperature. With that knowledge in hand, I knew just putting a structure over my plants wouldn't work, and I began researching some means of inexpensively heating the greenhouse. The first and most obvious solution to the problem would be to do what the rest of the world does: utilize some form of fossil fuels. Propane and natural gas heaters are relatively inexpensive, easy to install, and easy to find and source. Need to make a bigger temperature difference between the inside and the outside? You simply buy a bigger heater and burn more fuel. However, I ruled out in my case a propane heater for a few reasons. First, I just didn't feel right about burning fossil fuels when compared to some of these other options I'll discuss, and I didn't like adding CO2 emissions when they could perhaps be avoided. I also didn't like the added expense. While propane heaters are inexpensive up front, I didn't want to spend what I had calculated would take likely thousands of dollars of propane each year to prevent damage to my plants and give me the head start and the longer season that these fruits needed. In fact, at this point we were running our farm, so I did some calculations, again, nerdy superpower of spreadsheets, to determine my yield on fig trees grown in the greenhouse. Using propane as a heating source would significantly reduce or even eliminate my ability to make a profit on these fruits. So fossil fuel heating was a no-go. But if not this conventional solution, then what? The next solution I took a look at was row covers. I'm a a big fan of solutions that don't require additional energy inputs. What if we were to put row covers in the tunnel over plants for the winter, at least on the really cold nights, in order to give them some extra protection? Plus, row covers are relatively inexpensive and can be used for a number of years, especially if the heavier weight ones are used. Unfortunately, row covers suffer some of the same problems as greenhouses themselves. While they may make a few degree difference, it's simply not enough for really cold nights or to prevent really hard freezes. We sometimes get stretches for days with little sunshine and very long, cold, single-digit nights. Row covers just didn't retain enough heat to make enough of a difference in our particular climate. Also, what happens if the crop wakes up too early? It's not unusual for us to get a warm week in the beginning of spring that can wake up our plants. Once the plants are awake, they're typically far less hardy than when dormant, especially the tender new growth. Would row covers really provide enough protection from an early spring night in the teens after new growth had started? I didn't think so. Finally, row covers can be labor intensive, and as a small farm, we can't afford to be inefficient with our labor. So unfortunately, row covers were out as well. So then in my research, I came across the concept of using external thermal mass, usually in the form of barrels of water or of rocks. These were usually deployed in smaller greenhouses as well as much better insulated greenhouses. What do I mean by thermal mass? Really, anything that can heat up over the course of a sunny day and then slowly give back or release that heat at a later time is thermal mass. As a small example, think of a parking lot during the summer. Parking lot heats up during the day as the sun shines on it, then releases that heat even after the sun has set. As a larger example, think of lakes and oceans. The reason areas by coastlines or even the Great Lakes are more temperate than the surrounding areas has a lot to do with the moderating effect of thermal mass of that large body of water that protects those areas from getting as cold as areas that are more inland. The same sort of idea can be used within a greenhouse, though obviously on a much smaller scale in a smaller space. Barrels or tanks of water, typically painted dark colors, or rock walls built into the greenhouse, absorb heat from the sun on sunny days, then release it whenever the surrounding air is cooler than the thermal mass itself. This solution has a lot going for it in terms of being completely passive. You set it up once, then forget it, and it works passively for you. While this is a nicely passive form of heating, it typically doesn't get deployed on a commercial scale. Why? A few problems. First, external thermal mass eats up valuable greenhouse space. Greenhouse space is considerably more expensive than uncovered land, meaning that every square foot counts. Any space taken up by thermal mass is space that can't be used to grow plants and help pay for the structure. The amount of water in barrels or tanks required to make a big difference in temperature is significant. A few 50-gallon barrels aren't going to make a big difference in a nearly 3,000 square foot greenhouse like the one we hope to build. Second, you can't control when you draw on the energy contained in these barrels. Since this thermal mass is completely passive, it stores and gives off stored energy outside of your control. For instance, if you have a sunny day in the greenhouse and your water barrels warm up during the day, they'll still give off their heat when the temperature drops in the greenhouse, regardless of whether you needed them to provide the heat then or a few days from now when you entered a cold and cloudy stretch. And finally, external thermal mass is primarily concerned with a daily charge and discharge cycle. If you go through a cold and cloudy stretch of weather, thermal mass does very little to help warm the greenhouse because it hasn't had a chance to charge up. But once again, external thermal mass was ruled out. With two of the more passive solutions like row covers and external thermal mass ruled out, there weren't many other passive solutions to explore. However, if you've done any research of your own into greenhouses or researched anything in the passive solar greenhouse space, you've undoubtedly come across a variety of solutions like the Russ Finch style greenhouse of citrus in the snow faint, the deep winter greenhouse from the University of Minnesota, or the Chinese solar greenhouse. All of these designs are attempting to accomplish the same sort of thing, to compensate for the heat loss through the poorly insulated glazed or clear portion of the greenhouse by greatly insulating all the other walls of the greenhouse, either by somewhat conventional means or by burying or using thermal mass to insulate them. The only exposed surface is the sun-facing one, so in our northern climate is the south-facing glazing. Once again, this is an attractive solution because it functions similar to the external thermal mass, an upfront cost that functions passively. So why did we not go with a highly insulated greenhouse? A few reasons. First and foremost was cost. Adding a significant amount of insulation to a large structure is expensive. For instance, the deep winter greenhouse materials alone added up to around $30 per square foot. That's around 10 times more expensive than our first greenhouse when we built it back in 2017. And at a certain price, it's just not economically viable. Second was availability. None of these highly insulated greenhouses are offered as a kit option from any of the greenhouse manufacturers I looked into. It's possible that these types of structures may become available in the future, but for now, if you want to build one, you'll have to put together a kit yourself. Finally, many of these highly insulated structures are really built for the shoulder season and for winter growing. When the sun gets stronger in the spring and summer, many of these greenhouses are so well insulated that they require active ventilation, meaning exhaust fans or perhaps shade cloth to operate through the summer months. This is an issue that can be addressed, but unfortunately the greatest strength of these types of structures is also their Achilles heel. So mainly due to cost, we had to roll out highly insulated greenhouses like the Chinese solar greenhouse. With many of the passive or mostly passive solutions ruled out, we looked at another form of heating, heat pumps. Either air source heat pumps like today's mini splits or geothermal heat pumps are really attractive in the home environment due to their efficiency. However, the low insulation value and therefore the high heating requirement of a greenhouse would require either a large number of heat pumps or a simply massive system to cover the heating needs of the structure. Despite the efficiency, the lack of availability of such a system at the scale we required meant that the heat pump route was out. It may be that heat pumps in the future could be scaled to meet the needs of a greenhouse, and in that case they may be an interesting solution and one worth exploring. While I was researching the various means of heating greenhouses, I came across an interesting solution, the climate battery. I'll give you a spoiler, we chose to put a climate battery in our greenhouse. In order to appreciate climate batteries, let's step back and look at greenhouses and what they do at the most basic level. Greenhouses are at their core big collectors of solar energy. Similar to solar panels that take light and convert it to electricity, greenhouses collect heat from the sun's radiation. In fact, even in a climate like ours, if left closed, our greenhouse would overheat during the day for all but the lowest light portions of the winter, something like 10 months out of the year. Now imagine yourself in the middle of a sunny but cold February day. You're nearly 2 months past the winter solstice, so the sun is strong even if the outside weather hasn't caught up yet. If you keep your greenhouse closed, you may end up baking your plants. However, at night you know the temperature outside will drop below freezing. So in order to avoid frying your plants, you vent out the excess heat during the day. Then to avoid freezing your plants, you pump in extra heat at night. Wouldn't it be nice if you could take some of that excess heat from the day, somehow store it, and draw on it at night when the temperature drops? That's what a climate battery does. A typical climate battery will use the thermal mass of the soil beneath the greenhouse as a large thermal battery. That means that on sunny days we can charge up the battery and then discharge it on cold nights. How do we accomplish this? Through a network of underground tubing buried within the footprint of the greenhouse that functions somewhat like a radiator on a car, carrying warm greenhouse air through a network of piping through the use of fans. So when the greenhouse gets too warm, we take that warm greenhouse air and pump it underground through that network of piping. The comparatively cool ground accepts some of that heat and the air returns into the greenhouse cooler than it went in. In this way, the climate battery is charged. Then at night, when the greenhouse temperature drops and we want to heat the structure, we run the same fans to pass relatively cool air past relatively warm ground. The ground then gives up some of its heat and returns into the greenhouse warmer than it went in. So why did we decide to go with a climate battery? Let me give a few reasons, some primary and some that are simply side benefits. First and foremost is operating cost. Our first climate battery greenhouse, a greenhouse that's nearly 3,000 square feet in size, draws about 2,000 watts when it's running. That's the electrical equivalent of a bit over a room-sized space heater to heat and also help cool, more on that later, a really large space. By our estimates, the climate battery costs a fifth to a third the cost of a comparable propane heater, even when accounting for the fact that we have to run the climate battery twice, once to store the heat and another to draw it out. Second is automation and robustness of the design. If I can't have a completely passive system, I want one with as few moving parts as possible. Unlike many systems, the climate battery really only has one moving part, the fans. If a fan were to go out or stop working, there are others running as well, so we'd just be operating at a diminished capacity. And the replacement amounts to literally plugging in a new fan and setting it atop the inlet riser. The tubing we use is made for burial in the ground, so it's not going anywhere and there's nothing to break. The fans are operated by a thermostat that kicks them on automatically at a high and a low set point. So there's nothing for me to do except manage the set points depending on my goals for the season we're in. The third reason is a happy side effect of the system. Since the climate battery uses soil beneath the greenhouse's thermal mass, as the battery is charged, the soil warms up, providing the plants with a warmer root zone earlier in the season and later into the season than they would otherwise have. As a result, our plants get an earlier start and a later end than plants grown outside. Fruits like we're growing, as well as tomatoes and other sun-loving crops, definitely love a warmer root zone, as well as, or perhaps even more than, warm air temperatures. The fourth reason is another side effect, though one we primarily see through the late fall, winter, and early spring months, and that's cooling and dehumidification. Due to the way a climate battery works, our greenhouses have the ability to cool themselves during the winter. An added bonus that we've seen is that the greenhouses also dehumidify themselves during the cooling process due to the hot, humid air of the greenhouse hitting its dew point when coming into contact with the cool soil and the condensation dropping out. So all solutions have their drawbacks, and climate batteries are no different. I don't think any of these cons should keep folks from considering one, but it's important to know the benefits as well as the drawbacks. The first and most obvious drawback of the climate battery is the upfront cost and work to install it. A climate battery requires excavation, purchase and placement of tubing, as well as careful backfilling to avoid crushing the tubing. I don't consider myself particularly adept at construction or soil work, but we were able to build the first system with some simple tools and a little knowledge along with the help of a local excavator. Still, there's no getting around the fact that these systems are relatively expensive to put in and have a back-of-the-napkin calculated payback period similar to solar systems of 5 to 12 years, depending on how it's used, when compared to a similar propane-powered heater. The benefit to a system like this, though, is that during and after the payback period, the system should require little to no maintenance. In our 6 years of operating a climate battery greenhouse, we've only had a fan quit on us once, and that just required the replacement of a capacitor, so around a $10 fix. The second drawback of the system is that it does require some monitoring of the greenhouse to adjust the thermostat in line with the seasons. Since the climate battery indeed operates like a battery, we are conservative in drawing on it during the winter and push it harder later in the spring when we'll know we'll get enough charge from the sun. This monitoring means that we look at the soil temperature a couple times per month and set our thermostats accordingly. It's an activity that really takes no more than a minute or two a couple times per month, and we're often in the greenhouse far longer than that just to escape the cold. The third drawback of the system is that the climate battery isn't a source of limitless heat. We're not breaking the laws of physics here. Okay, a bit of a nerdy aside here, but it's useful. You may have heard that just a few feet below the ground, the temperature stays a constant X number of degrees. And that's true, but only in a qualified sense. The temperature below ground fluctuates seasonally, and only when you get to about 20 feet below the surface does it actually level out. Fun fact, the leveled out temperature is actually somewhat of an average of your yearly temperature and therefore varies depending on where you are in the country. Meaning the further north you go in the States, the colder it gets, and when you get to Florida or Texas, it stays much warmer. Anyhow, that normal ground temperature swing does happen in a climate battery greenhouse as well. In fact, we don't run our climate battery for much of the summer to charge it up for winter, simply because summer does that for us automatically. Conversely, in the winter, since the sun is a lot less strong, it's very easy to draw more heat out of the ground than we're putting in through the weak sun, which if we're not careful means we can actually draw down our greenhouse soil temperature to below that of the outside soil at the same depth. If we think of the soil temperature as the charge state of the battery, where maybe 80 degrees is 100% and 40 degrees is close to 0%, we can see that as we draw and draw on the soil for its warmth, we can actually get pretty close to depleting our energy reserves altogether and lose our source of heat. This is a bit of an oversimplification of what's happening, but I won't bore you with perhaps some of the other factors at play, perhaps in another video. So that's it for the pros and cons. As I mentioned, none of these cons kept us from installing a climate battery greenhouse on our farm. They're just some of the factors to consider when thinking through whether a climate battery is right for you. As I've mentioned, I like to research everything to death. So back in the mid-2010s, I tried to find out everything I could about climate batteries. Turns out the pioneer of climate batteries seems to be John Cruikshank, a gentleman who lived out in Colorado and ran the website sunnyjohn.com. Unfortunately, John passed away, but his legacy in climate batteries lives on. Being one of the first practitioners of climate batteries, there was a lot to figure out. Through the Internet archives, I was able to access John's FAQ about what he called SHCSs, or subterranean heating and cooling systems, what we now call climate batteries. In his FAQs, I learned the typical materials used in a design, primarily large culvert pipe and corrugated perforated plastic pipe, also called drain tile, as well as pragmatic guidelines on how to lay out a design. There was also a Sunny John calculator, an Excel spreadsheet that helped you design your own climate battery system with some of his rules of thumb baked in. And while I would differ on some of my design decisions now, these guidelines formed the basis of my climate battery knowledge at the time. Another invaluable resource when I was first starting out was a book called The Forest Garden Greenhouse by Jerome Osentowski. This book, full of beautiful photos of climate battery greenhouses as well as additional practical insights, helped also to form a basis for my eventual design decisions. I actually visited Jerome's farm and also the base of Crimpy, Colorado Rocky Mountain Permaculture Institute. Jerome's greenhouses really are as impressive in person as they are in the photos. While I am deeply appreciative of the work of each of the pioneers of climate batteries as well as the guts it took to experiment on these early systems, there are some rules of thumb that I learned from these sources that I would now only partially agree with. Some that entirely depend on your particular context, and some aspects of those earlier designs that need to be rethought. Stay tuned for my own thoughts later on in the video. So armed with all this information, we had some choices to make. Unlike the greenhouses in Colorado where the climate batteries got their start, I didn't want to build a highly insulated greenhouse due to the cost. Also, Colorado climate batteries were typically only excavated down to 4 feet, which limits battery size. In sunny Colorado, a smaller battery might not be as big of an issue, but what about in Pennsylvania where winters meant cold as well as cloudiness? And what about size? Many of the well-insulated greenhouses I had seen were rather small. How would a climate battery behave in a more conventional 30 by 96 foot structure? So in the late summer and fall of 2017, we broke ground on our first of 2 climate battery greenhouses, and still our best performing one, a 30 by 96 foot structure covered with double poly and polycarbonate end walls. The climate battery itself consisted of 3 individual systems, or cells as we would come to call them, each consisting of a fan that mounted vertically to a riser, which in turn connected to a manifold underground. Connected to the manifold were a series of pipes that ran at an angle across the width of the greenhouse and were each 30 feet in length. Those connected to another manifold and a riser on the other side, the outlet. All in all, we had over 4,000 linear feet of piping buried in the greenhouse in 30-foot sections, down to primarily a depth of 5 feet, but in some cases 6, 7, or even 8 feet. You can find further design specs for this greenhouse, which we unimaginatively and boringly call the Gray House due to its great cover over the door, at our website, threefold.farm, along with a 3D model. We finished building our greenhouse on top of the climate battery tubing in mid-November, actually during one of the first early wet snows of the year. Our desire was to grow figs inside the tunnel, but I wasn't sure what to expect out of the system. So that first winter we planted oats inside the tunnel, both as a cover crop and as a sort of canary in the coal mine, since oats have a similar kill temperature. That winter we hit -5 degrees Fahrenheit outside, and despite starting with a cold battery, a leaky structure, and not really knowing what we were doing, we were able to maintain 19 degrees Fahrenheit in the greenhouse and kept alive our cover crop as well as a sacrificial potted citrus tree that I had in there. So in the spring of 2018, we planted our first fig trees in the greenhouse, and they loved it. We were able to keep the figs growing and active late into the year, which meant we'd get a decent harvest next year. And that following winter, and in all subsequent winters, using the climate battery alone and no backup heat, we were able to overwinter figs with no noticeable damage. That year, we were ambitious and put up our second climate battery greenhouse, a 34 by 96 foot structure with a modified climate battery design. Without any real knowledge of physics we were playing with, we modified the design to be less expensive to build and hoped to match or exceed the performance of our first greenhouse. Over the next few years, with an increased knowledge of how our system performed, along with some performance tweaks by swapping out fans, we were gradually able to increase the number of frost-free days in the structure from 250 in 2018 to over 300 a day. In the winters of 2022 and 2023, our number of nights below freezing numbered in the single digits. In 2022, I had an idea. By then, we had a much better understanding of the physics of climate batteries and knew how far we could push them. And each winter, we were beginning to test how warm we could keep it. Figs always overwinter just fine. What if we could grow plants that liked it even warmer, like citrus and avocados? Some of the figs we had planted in the greenhouse grew well, but didn't fruit as well as we needed them to, so they needed to come out. In their place, we planted 7 citrus trees, 3 types of satsumas, which are a type of mandarin orange, as well as a yuzu lemon, 2 Meyer lemons, and a Persian lime. Additionally, we planted 3 varieties of Mexican avocados. While some took some adjusting to our slightly alkaline soils, all are now thriving in the environment and made it through their first winters without any damage, though we did baby the avocados through their first winter. With that success and the smell of citrus blossoms in the air, we decided to push the envelope even more. On a trip to South Florida at the Miami Fruit and Spice Park, I visit fruit trees on vacation as well. I saw some of the fruits that could grow there and was inspired. Could we grow bananas or star fruits or even mangoes? I wanted to try it out, so I began either sprouting seeds from the fruit I ate or purchasing smaller plants to try it out. The list of plants we are attempting to grow in the greenhouse is, frankly, getting a bit out long to cover here, so I'll put up a list and hope my esteemed video editor will splice in some clips of them happily growing in the greenhouse. To be fair, these fruits have only made it through a single winter, so it's honestly too early to tell how they'll do long term, but it seems that right now we can reliably create something like a mid-Florida climate. Pretty cool. Our journey with climate batteries hasn't been all sunshine and figs. We finished our second climate battery greenhouse in 2018 and realized it didn't perform quite as well as our first one, always running 5-ish degrees cooler. Why? Right as we were finishing up with our second climate battery greenhouse, I connected with a group of engineering students at a local university, Penn State Harrisburg. The seniors needed a project, and I needed to understand how these greenhouses actually worked from a physics perspective, so we partnered up. Over the course of the next few years in several groups, I gradually formed an understanding of our 2 greenhouses, what worked and what didn't, and how I could make the current systems better as well as improve future designs. So learn from my mistakes. here are 3 main takeaways and the 3 things we did to improve the performance of the existing designs. First, the existing 2 greenhouses, though they worked well and were far more economically efficient compared to a propane heater, were incredibly inefficient at distributing air evenly throughout the varied tubing. Why? Because the design mostly ignored the fact that air, which is a fluid like water, will take preferential paths. We found this out when some students, of their own accord, decided to climb down into the pipes and measure airflow coming out of each individual heat transfer tube. What did they find? A nearly 10x difference between the tube with the fastest airflow and the slowest airflow. Since we had discovered a positive correlation between the speed of the air and the rate at which heat moves into the soil, that meant that some of the tubes were doing most of the heat transfer work, while others, the ones starved for air, did almost none. In fact, we had something like the 80-20 rule going on, where 20% of the tubing was doing something like 80% of the heat transfer work. This meant that while our system was efficient, there was still a ton of room for improvement, both in the upfront cost and the ongoing operating cost. Second, we began to understand a bit about heat movement through the soil. Heat moves very slowly through the soil. In fact, it acts more like an insulator than it does a good conductor. We can use this to our advantage as we think about how close or far apart to space our tubing, both horizontally and vertically. Third, we began to understand the role that an effective fan plays in the system and how that cooperates with the design of the tubing. Ideally, the air should be distributed through the tubing as equally as possible, only moving fast enough to maximize the rate of heat transfer into and out of the ground while minimizing the cost to install and run the system. That's a lot to wrap your head around and a lot of things to balance in a design. So with those 3 takeaways from the Penn State groups, as well as our own observations, what changes have we made in the years since their construction? Well, 3 main things again. First, the climate battery fans. The fans we were initially guided toward and the ones we first installed in the greenhouses just weren't designed with a climate battery in mind. By switching out our fans with better suited ones, we were able to make a bigger difference in the greenhouse temperature during the winter, as well as the ability to capture more heat. Second, reducing heat loss. We now pay particular attention to any air leaks in our greenhouses that may mean we're losing critical heat to the outside. Better sealing all around may mean a few degrees difference. Additionally, we also built a seasonal windscreen that makes a significant difference when those cold winter storms flow in and draw heat away from the structure. This is called convective heat loss and is analogous to what happens when you blow over a cup of hot soup or coffee. I credit the windscreen alone with effectively extending the growing season by a month and drastically reducing our heat losses from those very cold winter storms that blow in. Third, we manage our climate battery better. In our climate, we begin pre-charging our battery starting in mid-September and are very conservative with spending any of that heat until we absolutely need it. We've also installed automated peak vents on our end walls to act as a sort of relief valve for the greenhouse during the seasons when it's critical to bank heat. That means that instead of opening a sliding door during a really sunny early spring day, we can leave the greenhouse closed up and allow it to regulate itself. First with the climate battery running, then the peak vent if it begins to overheat. By doing this, we can maximize the amount of the sun's energy that we can store in the soil for any single day. With all that we've learned about climate batteries through operation as well as formal study, in 2020 I was beginning to imagine what an improved design might entail. Could we design a climate battery that was more efficient at storing and retrieving solar energy while also inexpensive enough to make it pay for itself in a reasonable time frame? Could we address the major hurdles of unbalanced airflow, fan selection, economical design, as well as make a system that was scalable? That's when we launched Atmos Greenhouse Systems. Up to that point, climate battery design was progressing slowly because the cost to iterate was very high, and there was very little that could be done to tweak a design once it was in the ground. I was used to the software world where building and testing a change to a design could be done almost instantly and for very little cost. How could we do that with climate batteries? The answer came in the form of physics simulation software. CFD, or computational fluid dynamics, allows you to test fluid flow in a system before it's ever implemented in the real world. We therefore created a 3D model of our proposed designs, ran them through the software, and were able to see the airflow characteristics like velocity and airflow distribution without having to put a single tube in the ground. Neat stuff. So by using CFD, we were able to iterate through a number of designs to come up with one that we thought was the best compromise of cost to the farmer, distribution through the soil profile, and balanced airflow in the tubing. We also utilize heat transfer simulation software to visualize seasonal energy storage. Doing so allowed us to visually approximate how heat would move through the soil profile and determine if our piping was properly spaced. It also made for some really stunning visuals. From the beginning, we designed the system to be modular in the way that greenhouses are scaled. So if you build a bigger greenhouse, the design can scale with you. The result of all this is what I think are some really solid climate battery plans available at atmosgreenhouse.com. We provide the PDF blueprints that you can build with parts that are generally sourced locally, along with local excavators. If you're considering putting up a Climate Battery greenhouse yourself, even if you'd never considered purchasing our plans, I'd encourage you to take a look, if only for the resources available on our site and for things to consider as you're looking to heat your greenhouse. I've talked to a lot of people over the years about climate batteries, and I certainly don't recommend them in every instance. I actually discourage people in many instances if I think it wouldn't be a good application or wouldn't be economically wise. So take a look at our website or reach out to me if you have questions. If you stuck with me for this long, thank you. Climate battery greenhouses have a lot of potential in my book, and I'm excited to see where this progresses in the next few years. If you have questions or your own ideas about how to make climate batteries better or more accessible, let me know in the comments or reach out to me through threefold.farm or atmosgreenhouse.com. Thanks, y'all.